Autonomous software agents execute tasks at network speed. They scrape data, trigger logic, and route information across servers in milliseconds, interacting with the digital world far faster than human operators. That efficiency holds right up until an agent hits a financial paywall. To solve this friction, the X402 protocol turns the Stellar network into a native financial rail for the machine economy, allowing these non-human actors to execute rapid microtransactions over standard internet protocols. When an agent requests a monetized resource, the server intercepts it and returns an HTTP 402 payment required status code. The agent automatically evaluates the requested cost against its internal logic and cryptographically signs a payment authorization, all without human intervention. But settling these transactions on a public blockchain introduces a severe operational flaw. Every X402 payment becomes a permanent public on-chain event. The sender, receiver, exact amount, and timing are instantly visible to everyone. For an AI agent, this payment history is a transparent map of its operational logic. It broadcasts the agent's service dependencies, its behavior patterns, and its revenue cadence to competitors. For enterprise users managing fleets of these agents, this level of transparency is legally untenable. Exposing all payment flows makes it impossible to comply with GDPR data protection requirements or the confidentiality mandates of UCC Article 12 for digital assets. If every machine-to-machine payment requires forfeiting operational privacy, major institutions cannot deploy autonomous agents at scale. The payment rails work perfectly, but the transparent settlement layer creates a barrier to entry. To fix the privacy problem without abandoning the rails, developers built Spend_Private. It is a non-custodial, zero-knowledge, shielded payment pool deployed natively on Stellar's Soroban smart contract platform. It acts as an infrastructure layer that utilizes mathematical proofs to turn a fully transparent public ledger into a blind settlement layer. Observers can see that value moves, but they cannot link the sender to the receiver. This unlinkability is achieved through a strict three-stage pipeline. First, public tokens are deposited into the pool. Second, the user initiates a private spend off-chain. Third, the smart contract verifies and settles the transaction. To understand how the network can authorize a specific payment without knowing the payment's variables, we have to reverse engineer this sequence. True cryptographic anonymity relies on math to authorize a transaction while simultaneously blinding the ledger to the underlying variables, a level of security that goes far beyond simple name obscuring techniques. Securing a payment flow requires breaking the chain of custody at the very first step. The system must decouple the entity depositing funds from the entity eventually spending them. An operator begins by depositing standard public tokens directly into the Pakana smart contract pool. This initial transfer is entirely public, but instead of crediting a standard public account balance, the contract issues what is called a note. This note is a cryptographic commitment to the deposited funds. To construct the note, the system takes three specific inputs: the exact amount of tokens deposited, the depositor's public key, and a newly generated random secret. These three variables are fed into a Poseidon hash function. Poseidon is a specialized cryptographic algorithm optimized to process data natively over finite fields. It compresses the amount, key, and salt into a single, opaque 32-byte string. The smart contract takes this resulting string and appends it as a new leaf into an ever-expanding on-chain Merkle tree. The raw inputs are discarded. Anyone watching the ledger sees exactly how much money entered the pool, but once that value is represented as a hashed commitment inside the Merkle tree, its specific attributes are cryptographically locked. It becomes mathematically indistinguishable from every other deposit in the pool. That creates a new engineering hurdle. When the user wants to spend their funds, they have to prove to the smart contract that they own a specific note inside that Merkle tree without pointing to which note it is. The solution relies on the underlying mechanics of zero-knowledge proofs. Historically, these proofs operated as an interactive mathematical game played between two parties, a prover and a verifier. You can see the foundation of this concept in early cryptographic texts, which illustrate the protocol using the characters Peggy, the prover, and Victor, the verifier. In this interactive model, Peggy claims to know a secret. To test her, Victor asks a series of random, highly specific mathematical questions derived from the problem. If Peggy truly knows the secret, she can answer every single question correctly. If she guesses, she might pass one or two questions by chance. But after 10 or 20 random challenge rounds, the probability of guessing correctly drops to near zero. Victor is mathematically convinced she knows the secret, even though her answers never actually revealed it. The limitation is the required interaction. A protocol demanding constant back-and-forth communication works between two live servers, but it is entirely incompatible with the rigid asynchronous environment of a smart contract on a public blockchain. To deploy this technology on the Stellar network, the interaction had to be eliminated. The proof system needed an evolutionary leap from an interactive dialogue to a static, deployable payload. This page details the exact mechanism that makes that possible, the Fiat-Shamir heuristic. It solves the interaction problem by replacing the human verifier with a one-way hash function, acting as an unbiased random bit generator. Because the hash function's output is completely unpredictable but entirely deterministic, the prover can use it to self-generate the random challenge questions. This allows them to calculate the entire challenge and response sequence locally in one step, without a live verifier. Pakana maps this exact mathematical principle into its split-brain node architecture, separating the heavy computation from the network execution. All the heavy lifting happens off-chain. When an AI agent pays for an API call, its local interface, the satellite node, generates a non-interactive Groth16 ZK snark. It computes the proof using the secret note data locally. This compiled proof is a dense 320-byte payload. It allows the agent to mathematically assert ownership of their locked note and authorize its transfer without transmitting a single identifiable metric to the public ledger. That level of opacity creates a severe network vulnerability. If the smart contract verifier doesn't know which specific note in the Merkle tree is being spent, there is nothing stopping a user from spending that same note multiple times. To prevent double spending without breaking privacy, the system introduces a cryptographic constraint known as a nullifier. A nullifier is a deterministic, one-way hash derived from two specific elements, the original note's serial number and the spender's private key. When the smart contract receives the zero-knowledge proof, its first action is to evaluate the attached nullifier. It checks a registry of previously spent notes. If the nullifier is already in the registry, the contract instantly reverts the transaction, preventing the double spend. If the nullifier is clean, it is recorded, and the contract moves to its second action, verifying the dense mathematics of the Groth16 payload to ensure the spend is authorized. Doing this entirely on-chain was historically impossible. Processing complex BN254 elliptic curve pairings inside an isolated WebAssembly environment caused extreme code bloat. The metered execution costs routinely exceeded network gas limits, making the verification economically prohibitive. That limitation was removed by the Stellar Protocol 25 network upgrade. The upgrade took those complex cryptographic primitives and embedded them directly into the core C++ host environment of the Stellar node via a native host function. By elevating the pairing check to a native host function, the computational friction is bypassed. Complex zero-knowledge verification transforms from an academic theory into a highly efficient, high-speed reality. When you combine the off-chain proof generation with the on-chain native verification, you get a complete end-to-end shielded architecture. An autonomous AI agent initiates an X402 micropayment by generating the ZK proof entirely on its own local hardware. This enforces a strict compute outside, verify inside model. To ensure the agent's public wallet address isn't exposed by submitting the transaction, the compiled proof is passed to a final architectural component, the primary node, acting as a relayer. The relayer intercepts the proof, submits the final transaction to the Stellar network, and pays the native gas fee on the agent's behalf. The agent never needs to hold public network tokens to operate. From the perspective of the public ledger, the only visible action is the primary node interacting with a smart contract. The agent's identity, the service provider, and the transaction value remain completely hidden. In the final settlement phase, the smart contract validates the proof and issues the recipient a brand new, mathematically unlinkable output note. The payment clears instantly with zero public linkage. By fusing off-chain Groth16 proofs with Protocol 25's native host functions, Pakana solves the transparency paradox. They built the secure, compliance-ready privacy layer that the autonomous machine economy requires to scale.